I would start today's lecture with several examples of random variables that follow binomial distribution, and we will discuss how for each of those examples these four properties are satisfied. Muhammad Faris.
Yes, doctor, I have a question, please. Tries are independent. I don't understand this point.
That means you perform the experiment one time and then another time. These two times are independent. I will explain it where this property is not satisfied. You will get the point when I give you an example where this property is not satisfied.
Okay, thank you.
Any other question? Far as by the end of today's class, if you still don't get the point, let me know.
Okay.
So let me repeat the four properties. Usually a binomial experiment is based on selection. You have a sort of population, and in this population you have either finite or infinite elements. A very big number of elements. Each of these elements is considered as either success or failure, and you select some of these elements. For example, you pick some of them like this one, success or failure, and you pick this one, success or failure, and so on. You pick this one, success or failure. So from the population, you pick n. Now, if the selections are independent of each other, every unit is categorized as either success or failure. You are selecting n items. You know you are selecting n items, and the probability of success remains equal for every selection. In that case, in this sample of n items that you picked from that bigger population, if you denote X by number of successes in this sample, then X follows binomial distribution. Now, before I go towards several examples of binomial distribution, I would like to continue. What if X follows a binomial distribution? If X follows a binomial distribution, you can easily write the probability mass function of X like we did in a uniform distribution. You can easily write the probability mass function. You can easily write the mean expression. You can easily write the variance expression. So if X does follow a binomial distribution, the probability mass function of X, that is n combination X multiplied by p to the power X multiplied by 1 minus p to the power n minus X, where X can be 0, 1, 2, all the way up to n. So you are selecting n objects. The number of successes out of those n, you may get 0 success, you may get 1 success, you may get 2 of them successes and remaining failure, and you may get all of them successes and no failure. So the possible values of X, which is number of successes, it can be from 0 all the way up to n. Now in this probability mass function, you see other than X, there are two unknown constants, and these two unknown constants are called the parameters of binomial distribution. And these two parameters are n and p. These two parameters will come from the question. That means from the question you have to identify what is n and what is p, where n is the number of times, number of selections, I would say, and p is the probability of success. Once you plug the values of n and p into the question, the only thing that will remain unknown in this function will be x. So it will simply be a function of x. You can just put the value of x and you will get the corresponding probability. Similarly, if you are able to identify that x is binomial, you can simply use this expression for the mean. It's n multiplied by p. Also, if you're able to identify that x is binomial, the variance can be easily found by simply plugging in the values of n and p in this expression. So whenever you see a question from binomial distribution, there can be three tricks in that one. Number one, you will be asked to identify what is the distribution of that variable. So from the properties of the variable, you should be able to recognize that x has a binomial distribution. Once you are able to recognize that x has a binomial distribution, you need to get these two constants from the question, n and p. Once you see all four properties are satisfied, you should be able to identify from the question that how many times we are repeating the experiment and what is the probability of success. These two will be constant values. Then you just plug in these values in this function, the probability mass function, and you will have a function of x. Then the question will either ask you for the probability. If the question asks you for the probability, you just plug the values of x in the function and you will get the probabilities. Or the question will ask you for the mean or variance. So in that case also you plug the values of n and p in the expressions and you get the mean and variance. Let me copy several examples from your book. Of binomial random variables. Okay, I copied 7 examples from your book. Let's look at these examples one by one. Example number 1. You flip a coin 10 times. And x denotes the number of heads you obtain. After flipping the coin 10 times, out of 10, how many heads are you getting? That is x. Now let's check the properties one by one. Before performing the experiment, do you know how many times do you have to perform the experiment? Yes, you have to perform the experiment n times, which is 10. Every outcome of the experiment, does it have only two possible outcomes, success or failure? Yes, it has only two possible outcomes, the success and failure, and the success is head. This is your success. This is where you are interested. Is the probability of success constant for every trial? Every time you flip the coin, is the probability of success constant? Yes, the probability of success is half, and every time it is half. Every time you flip the coin, the probability of success is half. Second time you flip the coin, does it depend upon the result of first trial? What was the result of first trial? For example, first time you flip the coin, you got a head. Then When second time you are flipping the coin, whether you are getting head or tail, does this depend upon the first trial? No, the trials are independent of each other. Ahmad Ismail, please go ahead.
No, just wanna say no. Independent.
Yes, exactly. Independent trials. So all the four properties are clearly satisfied here. This means your X has a binomial distribution here with n equals 10 and p equals half. Now from this example, I can ask you any question. I can ask you find the probability that you will get 5 heads, find the probability that you will get at least 9 heads. I can ask you any question. And later I will pick one of these and go on towards solving the questions. The difficult part is this, the one I just did. Look at the question and try to see if the properties of binomial are fulfilled. Later I will tell you the shortcut method of identifying also. Second example, a Warren machine tool produces 1% defective parts. Let X denote the number of defective parts in next 25 parts. So X is the number of defective in next 25 parts. So let me highlight the important information, next 25 parts. So the experiment is you will check next 25 parts one by one. You will see either the part is defective or not. And there is 1% defect rate of the machine. This is all the information we have. Let's check the properties one by one. Do we know how many times we have to perform the experiment? Yes, 25 times. Whenever we perform the experiment, each time, do we have just two categories, success and failure, where success is where you are interested and you are interested if the object is defective. By the way, this is the success. Each time, do we have success or failure as two possible outcomes? Yes. What is the probability of success? Your success is that the part is defective and the probability of defective is 1%. Is this constant for every time you perform the experiment? Yes. For every object, the probability of being defective is 0.01. Let us say you picked first object and it was not defective. Now, when you are picking the second object, does the result of second trial depend upon the first one? No. So independent trials. That means, yes, here X follows binomial with n equals 25 and p equals 0.01. Muhammad Faris.
Doctor, here with replacement.
I will get to that. I will get to that.
Okay.
I will get to that. Let me complete these 7 and then I'll get to the shortcut method. That when specifically we get the experiment to have a binomial experiment. Third example. Let me finish these quickly. Third example, each sample of air has 10% chance of containing a particular rare molecule. X is the number of air samples that contain a rare molecule. Now I'll not write anything down there. I'll just directly write what is the distribution of X. Each sample has a 10% chance. So this 10% chance of containing a rare molecule, this is the probability of success. X is the number of successes in next 18 samples. So clearly your X follows here a binomial distribution with n equals 18 and p equals 0.1. Why? Let's check. Number one, do you know how many times do you have to repeat the experiment? 18 times. Yes. Number two, for every trial, do you have two possible outcomes? Yes. Either the sample will contain particular molecule or it will not contain particular molecule. And you are interested in event that it will contain particular molecule. That is your success. Is the probability of success constant every time you pick the sample? Yes, it's 10%. Are the trials independent? Yes, they are independent. So in that case, if you denote X by the number of successes, it has a binomial distribution. Number 4, of all the bits transmitted through a digital transmission channel, 10% are received in error. X is the number of bits in error in the next 5 transmitted bits. So for number 4, X has a binomial distribution with N is 5 and P is 0.1. Number 5, and this is of your interest. A multiple choice test contains 10 questions. Each has 4 choices and you guess at each question. And this will be the case in midterm exam. Let X with 5 choices, by the way. Let X be the number of questions you answered correctly. So X here follows binomial with N equals 10 and P equals what? Who can tell me what will be the P here? Each question has 4 choices and you are simply guessing each question. Nawaf Ali.
0.25.
0.25. It has 4 choices, but you are interested in whether you are getting the right answer or no. So success is that you get the right answer, failure you don't get the right answer. And the probability of getting the right answer is 0.25. In this case, if there are 5 choices, that will be 0.2. 6. In next 20 births at a hospital, X be the number of female births. So here X follows what? Binomial with N equals 20 and P equals what? Who can tell me the P? Ali.
1/2.
1/2.
Half.
Half. Number 7. Of all the patients suffering from a particular illness, 35% experience improvement from a particular medication. In the next 100 patients administered this medication, let X be the number of patients who improve. What is the distribution of X? Binomial. Who can tell me N?
100.
100. Faris, what is P?
0.35.
0.35. What if I ask you the question, let X be the number of patients who do not improve, What will be the distribution of X in that case?
1 minus 0.35.
Will the distribution still be binomial?
I don't understand your question.
What if I ask you the question, let X be the number of patients who experience no improvement or who do not experience improvement?
Yes, doctor, it's binomial.
It will be binomial with parameters what? Will N still be 100?
1 minus 0.35.
Yes, that is the only thing that will change. N will still be 100, but the P
Yes.
will be 0.65. P will change and it will be 0.65. Okay, in all those examples, you must have noticed one thing, that every time we're talking about binomial distribution, we are talking about selections. Selections out of a specific population. Now, a shortcut method for identifying if the experiment is a binomial experiment is try to look at the question and see you're selecting out of a population. You're making n selections. This is a population of success and failures. Many of them. Maybe finite, maybe infinite. If you're selecting with replacement, and the question clearly says that this is with replacement. And from here, by the way, you define X as number of successes. If you select with replacement, then X will be definitely binomial. Because when you're selecting with replacement, you're putting the item back before picking the next one. So the population size remains same. And it does not affect the probability of success, and the trials are independent. That is the first shortcut. The second shortcut is selecting without replacement, and this will be the most commonly used case, because in most of these examples you don't see the question saying with replacement. So as we said in chapter 2, when there is no discussion about with or without replacement, we assume the default case, and the default case is what? The default case is without replacement. So in all these questions where we don't see any information about with or without replacement, you will be assuming that you are picking without replacement. But when you are selecting without replacement from a population of size infinite, if the population size is infinite, even if you are picking without replacement, it will not make a difference on the population because the size is too big or infinite. So if I have infinite number of patients in my population and I pick the first one, the probability that he will recover from the medication is, let us say, 35%. And then I pick another one without replacement. It will not make a difference on my population. Why? Because it's a huge size, infinite size. Even in this case, in second case, X will still be binomial. For the third case that I'm going to discuss now, this is where binomial fails. You are selecting without replacement from a finite population, and clearly the population size is mentioned in the question. In this case, X is not binomial. So this is the shortcut. X will follow another distribution here in the red color, what I marked. There is another special distribution that we will discuss later. X will be following that distribution, but this is the overall map. Now, before I get to Faris, the question asked by Faris, what do I mean by infinite and finite here? If the population size is mentioned in the question, it is finite. If it is not mentioned in the question, it's assumed to be infinite. Yes, Faris, go ahead.
Yes, you answered my question. So
Okay.
in this question, because we didn't mention because it is so it is infinite.
Exactly. If the question does not say anything about from out of how many you are selecting, you'll assume it infinite. For example, in number 7, you are selecting 100 patients. Out of how many, we don't know.
Oh, out of how many? Yes, but
Out of
if
how
he
many, we don't know. So that's infinite size of population.
if he like put a number like 10,000 or
If
a
he
huge
says
number.
that out of 1,000 patients or 10,000 patients, you select 100, that's still finite. Even 1 million is finite.
Okay, clear now. Thank you.
Example number 4, of all the bits transmitted through a digital transmission channel, 10% are received in error. Let X be the number of bits in next 5. You are selecting 5 out of how many? We don't know. We don't know how many bits are produced by this channel. So that's an infinite population size. Muhammad Ali.
In part number 6, did you assume with replacement or without replacement?
If the population size is infinite, it doesn't matter if it is with replacement or without replacement.
It is finite.
If it is finite, then yes, it matters. If it is with replacement, still it will be binomial. Like I gave you example in the previous class. Here, you have a finite size of population, 10 items, and you're selecting 4 out of them with replacement. This was still binomial because you are selecting with replacement.
Okay, doctor, he didn't mention in the question.
No, I did mention that you are selecting 4 out of 10. This is the population size 10.
No, I mean in part 6.
About?
The example number 6.
Example number 6. Let me go to example number 6. In next 20 births at the hospital, let X be the number of female births. So in the hospital, you are selecting next 20 babies. Out of how many babies? How many babies are born in that hospital in the past, at present, and in the future? Infinite babies. You're selecting 20 out of them. So it's infinite size. Now, when the population size is infinite, it doesn't matter if it is with replacement or without replacement.
Yes,
and by the way, in this specific question, because they are not mentioning, so you will assume by default it is without replacement. All the questions where they are not putting anything about with or without replacement, you will assume without replacement. Example number 1, you flip the coin 10 times. So this is a sample of size 10. How many times can you flip the coin? You can flip as many times as you want. So this is coming from a population of infinite size. So basically what I'm saying is,
Doctor.
Yes.
What about question 5?
Question 5.
In the exam, he said will be 10 questions only.
A multiple choice question of 10 questions. Now you are selecting. I'm giving you 10 questions to answer.
Yes. It's finite.
Out of a pool. No. This 10 is always finite. Out of a pool of how many questions? How many questions do I have from which I'm giving you 10 questions?
He said 10.
I'm selecting, let's say, these 10 questions. Some of them I'm picking them from the book. Some of them I'm picking from the old exams. Some of them I'm creating the new questions. Now, can you tell me how many questions do I have in my pool?
Infinite.
You don't know, right?
Yes.
And the size is not mentioned. You are picking 10, but out of how many you don't know. So that means you are picking out of infinite those 10 questions.
Okay, yes. Get it.
Okay, let us pick one of these questions and solve it further. Let us pick this question number 5. This is interesting. This is more related to your midterm exam. A multiple choice test contains 10 questions, each with 4 possible answers, and you guess at each question. And X is the number of questions you answer correctly. So let me go ahead with example 4. Your N is 10. Your P is 0.25. Your X is number of correct answers. And your X follows a binomial distribution with n equals 10 and p equals 0.25. What if I ask you find the probability that a student guessing all questions gets 3 correct answers? So this is a very simple question. You are interested in probability that X is 3. So what will you do? You'll just plug the value x3 inside the mass function. By the way, I did not write the mass function. The mass function of X, I'm going to write it here, preferably with a different color. That is n combination X, p to the power X, 1 minus p to the power n minus X. Now you see when I plugged in the values of n and p, now this function is specifically a function of X. There is no other unknown constant. It's just X that is unknown. And what will be the domain of X? The domain of X is from 0 to n. So that means from 0, 1, 2, all the way up to 10. So you may get 0 correct answer, you may get 1 correct answer, 2 correct answers, you may get all 10 of them correct answers. So what is the probability that you will get 3 correct answers? The answer is simple. You plug 3 in this this mass function. So that will be 10 combination 3, 10 combination 3, 0.25 to the power 3, 0.75 to the power 7. And you will have the final answer. I may ask you probability that a student guessing all answers gets at least, or let's say less than, I would say less than first, less than 3 correct answers. So what are you interested in? Who can tell me? Raise your hand. Ali Abdul Rauf.
We are interested in 0 correct answer and the 1 and the 2.
0, 1 and 2, that means less than 3. This is probability of X equals 0 plus X equals 1 plus X equals 2. Not including 3, so you will not add 3 here. Now there is no shortcut way of getting the sum of this. You will have to plug in the value 0, 1, 2 separately one by one. So that will be 10 combination 0, 0.25 to the power 0, 0.75 to the power 10, plus 10 combination 1, 0.25 to the power 1, 0.75 to the power 9, plus 10 combination 2, 0.25 to the power 2, 0.75 to the power 8. And this will give you the answer. The probability of getting at least 1 correct answer. Raise your hand if you know what is required in this question. Muhannad.
It will be from 1 all the way to 10. Probability of 1, 2, 3, 4, all the way to 10.
All the way up to?
10.
10. Very right. So this is a lengthy question. You'll have to find probability of X equals 1, X equals 2, X equals 3. you have to find 9 probabilities, 10 actually 10 probabilities. Anyone who can tell me a shortcut way of solving this question?
Yes, Doctor. Probability of 0, 1 minus 0.
You can make use of which rule? Which rule you're using here?
Oh, forgot.
Who can tell me the rule that you're using here? Ali Abdul Rauf.
The complement rule.
Complement rule. This x greater than equal to 1 is an event. What is the opposite of this event? That x is less than 1. And the only value of x that is less than 1 is 0. So make use of the complement rule and you write this one equals 1 minus probability of x less than 1. And these two events are complements of each other. This one, not the probability expression, this event x greater than 1 and this event x less than 1. These two are complements of each other. So probability of A equals 1 minus probability of A complement. So I can write it equal to 1 minus probability of x equals 0. So that will be 1 minus 10C0 0.25 to the power 0, 0.75 to the power 10. So that's a shortcut way of getting this probability. What is the average number of correct answers? What am I asking in this question? Muhammad Faris.
The mu.
The mu. I'm asking for the mu. Now, there is a shortcut way of getting the mu if you are able to recognize that x has a binomial distribution. And just for you to verify that this shortcut way is nothing, but it also satisfies the actual definition of mu, that is summation x times f of x. So if you want to use the actual definition, you'll get the same answer. But because you are able to recognize that x is binomial here, better you use the shortcut way. So the expected value of x is, the expression will be given in the formula sheet and I will post the formula sheet by today evening. And this is equal to NP. So N is 10, P is 0.25. So the expected number of correct answers is 2.5. What is the standard deviation of so you're interested in sigma of x. And the sigma of x is the square root of NP into 1 minus P. It's the square root of variance. So it's 10 times 0.25 times 0.75 whole square root. And you will report the answer rounded up to 4 decimal points. These are all the possible questions you can expect from binomial distribution. Let me check. You can expect less than probability, less than equal to probability, bigger than probability, bigger than equal to probability. These 4 equal to probability. You can expect one of these 5 questions from probability. You can expect the mean, you can expect the variance or standard deviation. I think these are all the possible questions you can expect. Yes, these are all the possible questions you can expect from binomial distribution. Now at this point, if you have any questions regarding binomial distribution, raise your hands. Again, whenever you will get the question from number of selections, you will refer to this map. If the number of selections are with replacement, straight away the number of successes will be binomial. If the selections are without replacement from an infinite population, X will still be binomial. And if the selections are without replacement from a finite population size, then X will be binomial. Then X will follow another distribution that is called hypergeometric distribution, and that is our next special distribution for a discrete random variable. That is the third special distribution. By the way, I skipped one of them, the negative binomial. I will discuss it later because this hypergeometric is more closely linked to binomial, and we are already discussing the third case now. So it's better to get done with the hypergeometric first. So if you have an experiment where the interest is picking some objects, picking n objects without replacement out of capital N objects, and you define X as number of successes, the same number of successes, then this X follows a hypergeometric distribution. And this one has 3 parameters. Unlike binomial, it has only 2, n and p. You have to recognize the 2 values n and p from the question. This one has 3 parameters. There is small n, there is k, and there is capital N. And what are these? Small n is the number of selections. Capital N is the population size, which you are saying is finite this time. And capital K is the number of successes in your population. And if you are able to recognize that X is hypergeometric, you can simply write the probability mass function of hypergeometric distribution, which is f of X equals K combination X, n minus K combination small n minus X over n combination n. Where X starts from this number all the way up to this number. The mean is nk over n. The variance is nk over n times 1 minus k over n times n minus n over n minus 1. And these expressions will be given in the formula sheet. All the things that you see currently on your screen in the green color, all of these will be given in the formula sheet. You will be able to recognize from the question what is n, what is k, what is capital N, and what is required. Let us have a question. Let me copy a question from your book and then we'll solve it. This is example number 3.27. I'm picking from the book. Example 3.27. So here is the example. The example says that there is a batch of parts contain 100 from a local supplier of tubing and 200 from a supplier of tubing in the next state. If 4 parts are selected randomly and without replacement, what is the probability? Even if he does not say without replacement here, you will assume they are picking without replacement. So it's not necessary that it's clearly mentioned in the question without replacement. Default case is always without replacement. If 4 parts are selected randomly, I'm going to highlight the important information. A batch of part contains 100 local objects and 200 from another supplier. If 4 parts are selected randomly and without replacement, what is the probability that they are all from the local supplier? So basically in your population, you have 300 objects. The population size from here, your capital N is 300. Out of these 300, some of them are successes, some of them are failures. What is successes where you are interested? Look at the question. You are interested in the probability that they are all from the local supplier. So that means the local supplier objects are your interest. So that means your K is the number of successes in your population, which is 100. And finally, how many tubes are you picking? That means you're picking 4, N is 4. Now here, if you define X as number of parts from local. So here X will follow a hypergeometric distribution with small n equals 4, capital K equals 100, and capital N equals 300. Now, if you look at the question says find the probability that if 4 parts are randomly selected, all of them are from the local supplier. So the question says probability that X is 4. All of them are from local supplier. This is the question. So to solve this question, you will simply write the probability mass function of X. So when I say X has a hypergeometric distribution, let me write down the probability mass function of X here. The probability mass function of X will be, I would better write it f of X. That will be K combination X, N minus K combination N minus X over capital N combination small n. Where X can be, now I'm going to put the values here, where X can be from this value to this value. Let me plug the values in and I will show you what is the minimum value of X and what is the max. Don't be confused with this min and max. The max is the starting value and min is the ending value of X. Let me copy it here. And now I'll plug in the values of N, K, and see what happens. X starts from maximum of 0, N is 4, K is 100, minus capital N is 300. And it will go all the way up to minimum of small n is 4, K is 100. So maximum of 0 and what is this? 104 minus 300. What is 104 minus 300? 196. Is it? Or minus 196. And all the way up to minimum of 4 and 100. Now, who can tell me what is the maximum out of these two numbers? The two numbers are 0 and minus 196. Which one is maximum?
0.
0. So x will start from 0 all the way up to, there are two numbers 4 and 100. Which one is minimum?
4.
4. So your domain of x is 0, 1, 2, 3, all the way up to 4. That's the domain of x. This is how you get the domain of x in hypergeometric, and this is tough. So here x is 0, 1, 2, 3, or 4. Now you're interested in probability of x equals 4. So that will be simply 100 combination 4, 200 combination 0 over 300 combination 4. And you will get the answer, which you will report in your exam rounded up to 4 decimal points. Mohammed Shafiq.
What you did, Doctor, in the domain? I didn't understand.
To get the domain, x obviously is a discrete random variable which will start from one value and end at one value, right? To get
Yes.
the domain, x is starting from a value to another value. Now, if I tell you that x is starting from 4 to 10, you can write the domain, right?
Yes.
You will write it 4, 5, 6, 7, 8, 9, 10. If I tell you it is from 100 to 200, you can write from 100, 101, 102, all the way up to 200. So to write the domain of a discrete random variable, you need the starting point and you need the ending point. Now for hypergeometric distribution, it's not easy to get the starting and ending point. It is from this formula. This is the starting point. You plug the values of n, k, and n inside and you'll get the starting point of the domain. So when I plugged in the values of n, k, and n, and finally I went up to the last stage, I got maximum out of two numbers, 0 and 196, negative 196. Out of these two numbers, 0 is maximum. So the answer of this one was 0. Let me erase this one. This one was 0. This one came out to be 0. So the starting point of my domain is 0. The ending point is here on the right side. Minimum out of 4 and 100. You have two numbers, 4 and 100. Which one is minimum?
4.
4. So this is the ending point of your domain. So now you can write down the domain 0, 1, 2, 3, 4. Ali Al Hassan.
Yes, Doctor, we can find the probability by the counting technique, yeah?
Yes. All these distributions are coming from basic concepts of probability. This is basically without replacement, without order case. Ali Abdul Rauf.
Yes, Doctor. Why did we pick x to be 4?
We picked x to be 4 because here the number of selections are 4. Let me highlight it with a different color. If 4 parts are selected randomly, can you see it now?
So it's always the small n is equal x.
Small n is not always equal x. Small n is the number of pickings, and luckily for this question, it was equal to x. I could have asked you the question, you pick 4, what is the probability that 3 of them are from local supplier? Here the question says all of them are from local supplier. All means all 4 of them.
Okay, I get it now. Yes.
I could have asked you a question that none of them from a local supplier, so that means small x is 0.
Thank you.
So this last thing that I highlighted is basically the question. This is the question. So luckily the green and the blue thing came out to be same in the question, but it's not always that they are same. I can ask you for the average number of objects from local supplier. So I can ask you for the expected value of X, the average value of X. That will be 4 times 100 over 300. I can ask you for the variance of X. That will be 4 times 100 over 300 times 1 minus 100 over 300 times 300, that is capital N, minus small n over capital N minus 1. So you just have to plug the values in the expression and get the mean and variance. Muhammad Shafiq.
Doctor, I can find from the question the domain without this formula, right? Because
Yes,
there are four.
If you are able to recognize, yes, you can. Sometimes it's straightforward like binomial from 0 to 4, but sometimes it's not straightforward.
Okay.
To give you the example of that one, let's say you have a total of 10 objects in the box, 7 working, 3 defective. You pick 5 of them without replacement. So what is the distribution of X? Obviously X is hypergeometric here without replacement case and finite population. N is 5. K, let's say you are interested in number of working of let's say you are interested in number of defectives. So K is 3 and capital N is 10, right? Now, if you look at the domain of X using the logic that it starts from 0 to N, that will be wrong in this question. X cannot be 4 or 5 because there are only three defectives in your population. So here the domain of X will be 0, 1, 2, or 3. It will not be 4 or 5. So the ending point is not simply N. The ending point is minimum of small n and k, which is minimum of small n is 5 and k is 3. So the ending point is 3. In this example, the ending point came into the picture. Muhammad Faris.
Doctor, in a previous question, I didn't understand why we use a geometric distribution.
Hypergeometric distribution. Why we used hypergeometric distribution? Hypergeometric distribution is a distribution you apply when you are interested in a variable X, which is number of successes out of an experiment where you are picking some objects out of n objects without replacement. So whenever you are picking small n objects out of capital N objects without replacement, and you define X to be number of successes, X is always hypergeometric. So if you look at the question says that there were 300 parts in the box and you selected 4 of them randomly without replacement. So selecting 4 out of 300 without replacement, this is a hypergeometric random variable.
Okay, thank you.
Where did I write? Here. Picking n objects without replacement out of capital N objects.
We pick from finite.
Yes, you pick from finite.
If we have like the third case of binomial distribution, we use hypergeometric, right?
Exactly. This is where I wrote not binomial. This is basically hypergeometric.
Okay, clear now. Thank you.
Okay, gentlemen, if you don't have a question, you can leave the session at this point. If you have a question, raise your hands.